Afternoon session. Okay, welcome back to this afternoon session. And for the first talk, we have the pleasure of listening to Daniel Remenik from Chile, who will talk about KPZ fixed points part 2. So please.
Okay, thank you very much. And thanks for this invitation. So the plan for my talk today is this is a sort of continuation of Jeremy's talk from yesterday. So I won't go very much in detail about the KPZ fixed point itself. And what I want to do is try to show you some ideas of how we can get the KPZ fixed point as a limit from TASEP. So it's essentially, I'm going to show you some ideas about how we get explicit formulas for TASEP, and I'm going to explain these things and how they lead to this limiting Markov process, which is the KPZ fixed point that Jeremy was talking about yesterday. So very, very quickly, this is sort of a very quick summary of some of the things that Jeremy was saying yesterday. So we're looking at a class of models, which in particular include these interface growth models, like the Eden growth model or ballistic deposition, which are two that Jeremy discussed yesterday. And we are interested in the asymptotic fluctuations of these interfaces, which are growing in time. So they have this linear growth, and then you want to look at the fluctuations. And the main, or one of the main features of this KPZ universality class is that the size of the fluctuations have this special exponent t to the 1/3. And the spatial structure, the correlations are seen at this scale of t to the 2/3. So you see this in this Eden growth model, in the ballistic deposition model on the right. And then this KPZ universality conjecture could be stated as saying that if you rescale your height function, whatever corresponds to the height function in each of the models that you may want to be interested to look at, then with this 1, 2, 3 scaling, so this scaling of fluctuations with this exponent of 1/2, and then space is epsilon to the -1, and time epsilon to -3/2, that's the 1, 2, 3 scaling. Then if I rescale things correctly, I'm going to get convergence to this universal limit that we call the KPZ fixed point. Okay, and this is essentially what Jeremy was discussing yesterday and explaining some of the features of this process. Now, the models that I put here are extremely hard to analyze, and actually they have not been analyzed rigorously in any sense. So. Well, maybe I shouldn't say in any sense, but not to the level of these fluctuations. So we want to try to look at a simpler model, okay? And one of the basic models in the KPZ universality class is this very well-known TASEP process, the totally symmetric exclusion process, and sometimes also known as the corner growth model, as you'll see. So maybe let's start with the particle. There's two descriptions, or if you want, you can look at this in two different ways. One way is as the usual particle system. So this is very simple. You have particles which are evolving in the integer lattice. Okay, so we have this picture here, and you can only have one particle at every site. So at most, there's one particle at every site, and what the particles do is that they jump to the right independently at rate 1. But they're subject to this exclusion rule because you can only have one particle per site. Okay, so it's independent Poisson processes if you want, but they cannot jump on top of each other. Okay, very simple process. This is the totally asymmetric version because we allow particles to jump only to the right. There's, of course, you can allow particles also to jump to the left if you want, to the right with some rate, left with some rate. But that makes the process more complicated. So for now, we only want to look at the totally symmetric case, TASEP. Now, what's the relation between this and these sort of growth processes that we were looking at before? Well, you can very easily map this particle configuration to a height function. So the height function is the thing in red on top. And what's being done here is that above every particle, we are putting a little piece of slope 1, and then above every hole, we have a little segment of slope -1, okay? So then you get a picture like this. And then the evolution of the height function is simply that every time you have a local maximum, it turns into a local minimum at rate 1. Okay, that's exactly what this mapping on what these dynamics on the particles maps to when you look at the height function. Okay, so what you're going to see at the level of the height function is, in this case, an interface that's growing down. That's just a choice in exactly the same way as the particles are moving to the right. Okay, so this is the basic model that I'm going to discuss today. Well, probably most of you have seen this model before. It's very well studied for many different reasons. One thing that I want to note, because it's sort of implicit in what I will show you later, is that this particle system has the following property, that if you want to look at the evolution of the first n particles, then that only depends on those particles and it doesn't depend on anybody to the left. Okay, so when I look at the evolution of these first n particles, I don't have to look at anybody else, because this is because of the totally symmetric dynamics. Okay, so if I want to ask about the distribution of that particle, it's enough to look at the particle at the system with a finite number of particles, with n particles, and forget about anybody else. Okay. Okay, so that's TASEP. And well, as I was saying, this is a very well-studied model. So in particular, in the setting of the KPZ universality class, the type of thing we're interested in, which are these asymptotic fluctuations in this 1, 2, 3 scaling, are known for some special initial conditions since the, well, sort of the first one is from the early 2000s, and then the second one is sort of the middle of the decade. Okay, so just very briefly, the sort of thing that could be proved is the following thing. So for 2, or depending on how you count, for 3 or 6, but I'm just focusing on these 2. For these 2 very special initial conditions, explicit convergence could be proved. Okay, and the initial conditions are the following. So the first one is the narrow wedge initial condition, which I should have drawn it, but in terms of particles, it means that I'm starting with particles on the left and nobody on the right. Okay, so if you do that, then your height function looks like this wedge. And then if you run it for a long time, then what you see is something like this red process. And that's known as the Airy-2 process. Okay, so as t goes to infinity in this scaling, you get this Airy-2 process minus a parabola, which is the blue parabola. And this is one of these special stochastic processes that Jeremy was discussing yesterday. And in particular, this is the one where you see these Tracy-Witten GUE fluctuations. Okay, this is going to play an important. This initial condition is going to play an important role later on. And then the other one that could be done, and I'm going to more or less tell you how it was done, is the case of flat initial condition, which in terms of particles means this is a periodic initial condition for TASEP. It means you start with a particle and then a hole, particle, hole, particle, hole, and so on. And then as time goes by, you're going to see something which, well, now it's sort of it doesn't have a macroscopic shape. So it's essentially flat, but you have these fluctuations on top. And again, this is another one of these classical Airy processes. This one is called the Airy-1 process. And it is the one where you see Tracy-Witten GOE fluctuations. Okay, so these are the 2 initial conditions where you see these random matrix quantities show up. Okay, and the question is, the type of thing we want to do if we want to construct this KPZ fixed point, at least from TASEP, is to be able to do the same thing that I showed you here, but for general initial conditions. So we want to extend the class of initial conditions to much more than this. Okay, I hope it might become more or less clear what's special about these initial conditions, at least this one, and then I'm going to explain a little bit how flat is a little bit better. But the point, and what I want to discuss today, is try to show you some ideas about how you solve this in general. Okay, so for general initial data. So what I'm interested in, again, just to sort of recapitulate a little bit, I want to compute a probability such as this. Okay, so I want to compute the probability starting with some given configuration, now arbitrary configuration. I want to compute the probability that the nth particle lies to the right of some point A, okay? A statement, a quantity like this turns into a quantity for the height function, and then you can translate this distribution into a distribution for the height function, and that's the sort of distribution we need if we want to compute limits, okay? So this is really what I want to compute. Actually, I should, if I really want to take limits and get this whole process of the KPZ fixed point, I should be computing multi-point distributions, not just these one-point distributions. So I should be hopefully looking at several particles and try to see their joint distributions. And everything that I'm going to show you can be done for multi-point, but I'm gonna write things just for one particle because it makes life easier when I try to write things, okay? So that's the goal, try to compute a formula for that. So I'm gonna try to explain sort of the elements of this construction. And for that, I need to tell you some of the history of what has been done. So the first part of this history would be what's known as Schutz's formula. So this is a formula for the following quantity. So now I'm fixing the number of particles in my system. Okay, so I have n particles. And what I want to do is I want to start with particles at some locations y and ask for the probability that they end up at x. So literally the transition probabilities for my system, okay? And what Schutz found, using something called, an idea called, coming from physics, called the Bethe ansatz, is that these transition probabilities can be written in terms of a determinant, okay? So the formula, the transition probabilities from a set of positions y to a set of positions x equals the determinant of a certain matrix. And the matrix is built as follows. So you have this function f, which depends on, well, there's going to be some indices here. Of course, there's time. And there's these differences of positions, okay? And this function f inside is an explicit function. There it is, it's a contour integral, okay? So that's the formula. It looks mysterious a little bit. Well, it's not, depending on whether you have seen these things before or not, it looks very mysterious or maybe not so mysterious. But anyway, I want to sort of point out some elements of this formula. So the way the formula is proved is by using these Bethe ansatz, but it's essentially a way of showing that this right-hand side satisfies the forward equations for the system, okay? Actually, what the ansatz does is you sort of make a guess that it has to have a form like this determinant, and then what they do is they realize what the function has to be inside. But I want to make a comment about the function inside and why it's not so surprising that you would get a function of this form. So the function, so this function has this index here, I minus j, but in the case of negative indices, so when the index is negative for positive k, f of minus k, is actually not a completely, I mean, it doesn't come out of the blue. It's simply the Charlier orthogonal polynomials multiplied by the Charlier weight evaluated at a certain position, okay? So these Charlier orthogonal polynomials, what they are is that they are the discrete orthogonal polynomials, which are which are orthogonal with respect to this Poisson weight, okay? So that's just the Poisson distribution. And these orthogonal polynomials are the family of orthogonal polynomials with respect to that weight. Now, where does that weight come from? Well, it's simply the fact, so the Poisson weight is here because every particle, every free particle, if it had no exclusion, would be evolving according to a Poisson process. Okay, so that's really the reason why this weight is there. And when you want to compute when you want to check that this solves the Kolmogorov equations, the fact that you have this Poisson weight is going to enter into the picture in that way. Okay, so that at least tells you where this weight comes from. And then every orthogonal, or all these classical orthogonal polynomials satisfy certain recurrences. And the recurrence satisfied by the Charlier orthogonal polynomials becomes so it becomes that recurrence. And okay, this is very rough, but essentially this is going to turn into the boundary condition, which is representing the exclusion. Okay, so when the computation is done, this recurrence is essentially what's allowing you to check that particles cannot jump on top of each other. So somehow the structure of these Charlier orthogonal polynomials comes in a natural way when you want to check these Bethe-Ansatz computation from Schutz's form. Okay, so this is all very good, but the problem with a formula like this is that it's not really useful if you want to take n to infinity, this big N to infinity, because so number one, this is just transition probabilities, okay? And I would have to try to marginalize over the first n-1 particles, just to, and then sum over some positions to get something like what I'm interested in on top. But the big problem here is that I have this determinant which is growing with n. So as I try to take n to infinity, the determinant is growing, and I don't get something very sensible. So one has to get around that. So here's a separate fact, okay, which is not really using, at least in its, I think in its first proof, it wasn't really using Schutz's formula in any meaningful sense. So now for step initial condition, the one that I showed you, which for the height function looks like this, but where you put particles on the left and nobody on the right. So Johansson in the early 2000s got, well, and this is related to earlier work of Bike, Dave, and Johansson and other people. He got a formula like the one we want. Okay, so he got a formula where the right-hand side is now a Fredholm determinant. And this Fredholm determinant is, well, the determinant of I minus a certain kernel K. And the kernel K is what's written down here. And well, at least some elements from Schutz's formula are clear, because again, I have this Poisson weight and the Charlier polynomials appear again, but they appear in a very explicit way. Okay, so you just have to sum K from K equals 0 to n-1, the Poisson weight times the product of these Charlier polynomials. Okay, and what Johansson could use in this paper, is to now take this formula and compute the scaling limit that I showed you, the one that gives you this Tracy-Widom GUE distribution and one of these airy processes. Okay, so this is already of the right form, because you see, if I want to take n to infinity, n is only appearing as a parameter in a way in the kernel. Okay, so now if I want to take n to infinity, I just can take n to infinity inside the kernel, and well, you need some continuity, of course, but you're in good position to try to take limits. I'm not going to go over this, but I just want to point out that this is a special case. We're going to see why this is a special case, but it's a special case. There's many different proofs with slightly different flavors. The one that Johansson did, the first one, uses something called RSK, which is essentially an idea from combinatorics. There's a much later proof, or one could write a much later proof using a more probabilistic construction, which is what I'm highlighting at the end. And then there's another proof, which one can write down, which is what I wrote here as a trivial bi-orthogonalization. And that's what I want to discuss next, because that's how it's going to show up in the formulas that I'm going to show you. Okay, but essentially, the point I'm trying to make is that this is a very special case, and there's more than one way of proving this, and there's deep reasons why you get to a formula like this in this special case. Okay, so the next step in this story was taken by Tomohiro Sasamoto, and then Bordin, Ferrari, Prahofer, and Sasamoto a couple of years later. And what they wanted to do is use Schutz's formula to try to write down a general solution. So try to write down the general solution for TASEP, starting from Schutz's formula. And here, without saying too much, what they found is that you can do that. So you can go from Schutz's formula to a formula like that one, provided you can solve the following bioorthogonalization problem. And again, the Charlier polynomials are going to show up. So essentially, what I'm trying to say here is that you're going to get a formula like the one for step with a certain kernel inside, and the kernel comes from solving this bioorthogonalization problem. And the problem is you take these functions, the same functions as before, you shift them by the initial condition, and then you have to find polynomials of the right degree, which are bioorthogonal with this family of shifted Charlier polynomials. And well, what the first case you can do easily is exactly the case of step initial condition. So if you go through this with some care, you can check that essentially this shift by the initial condition puts you in a situation where these bioorthogonal functions which you're looking for, these polynomials, are exactly the Charlier polynomials again. So that's these phi's which you're looking for are exactly these c's over there. So that's the trivial case, because you're trying to bioorthogonalize something involving some orthogonal polynomials, but it's just the bioorthogonal polynomials themselves. Okay, and then what they could do in these papers is to solve the flat initial condition. I mean, the periodic initial condition, particle hole, particle hole, particle hole, essentially by linear algebra. Okay, so this is just a linear algebra problem, and in that case they could do it. But in general, there's no really linear algebra that's gonna, at least in a sense, linear algebra is not gonna give you the right the solution. Okay, so finding these phi's, it's not so clear how you should do it if you generalize to a general initial condition. So that's actually what we did in this paper with Konstantin Matetsky and Jeremy. So we could solve this bioorthogonal problem in terms of random walk heating times. It's not exactly what I'm gonna show you now, but essentially it's gonna be there. And once you solve it and you get these random walk heating times in the picture, you put it back in the kernel and you can start working with it. So I wanna try to give some idea of where this solution comes from, okay? So now, again, so I said that this solution involves some random walk heating times. So somehow you are able to bioorthogonalize using these random walks. I want to try to explain where that comes from. So there's essentially two ingredients in this proof. So the first ingredient is the following. So this is just a probabilistic fact about TASEP. So again, on the left-hand side, I am computing, I'm interested in the same probability as before. So now I start with some n particles, which are located at these points x1, x2, up to xn. And I want to ask, what's the probability that the leftmost particle is going to end up to the right of some position r at a later time. Now, if you think about it, due to the exclusion rule, if my particle xn wants to be to the right of r at times t, then everybody has to have moved to the right as well, right? Because the latest particle cannot overjump anybody else, right? So asking for the probability on the left is the same thing as asking for this particle to be to the right of r, the next particle to be to the right of r plus 1, and so on, right? X1 would have to end up to the right of r plus n, I guess. Okay, because otherwise there's not enough space for the last particle to jump where it has to jump to. But now you can imagine, and this is just a fact of the dynamics of TASEP being very symmetric, that this probability, the probability of everybody making these moves, is going to be the same as if I reverse time. And now I start with particles on the right, and I ask everybody to end up. So now I'm jumping backwards, and I ask everybody to end up to the left of these positions. x1 up to xn. So what I'm saying is that the probability that I'm interested in, this one, I can write as the probability for the reversed process to start at some configuration like this, where all the particles are packed, and end up to the left of those positions, okay? But the nice thing is that this is just, well, okay, I'm going backwards, but that doesn't change anything. So this is just TASEP with step initial condition. This initial condition here is exactly the one that I was showing you, that I was telling you that was easier to solve. Okay, so that's the first the first ingredient, and the second ingredient, and I'm going to go over this quickly, is that for TASEP with step initial condition, you see here I have my sort of step initial condition, but I also have a multi-point distribution. But there's an explicit formula. This is not how the formula was usually written, but one can write a formula like this. So actually, let me go one slide forward. So this also follows essentially, there's more than one proof, and it also follows essentially from different ways of seeing at the problem in the special case of step initial condition. What you have is that the probability that you're looking for involves the same kernel, which we already know, okay, times this factor over there. But the factor, it involves the following object, the one in red. So what you have is this Q appearing here are just, and this just sort of comes out of the formula. These Qs are the probabilities for the transition probabilities of a random walk with geometric steps. Okay, so these Qs here essentially come from the recurrence equation for the Charlier polynomials again. So inside you have these random walk transition probabilities, okay? And you have these projections chi, which are sort of killing everything below these positions A. So you have this formula, and you notice that the whole thing in red, what it is, it's just computing the probability for this random walk with geometric steps to stay above the curve given by the initial condition. Sorry, not the initial condition, the final condition. So you have these, you try to compute the probability that xt lies to the right of A for every I, and you solve the problem in terms of a kernel where what you have to do is compute the probability that a random walk is going to take some steps and stay above those points, okay? So that's the sort of thing you get. And well, now you can start sort of playing with this, because on the one hand, I started with what I want. I can write it in terms of TASEP with step initial condition. But then for step initial condition, I have an explicit formula which tells me that the sort of kernel that I'm looking at involves the heating times of some random walk, okay? So I'm going a bit slower than I thought, but here's the formula you get to. Using this, you can sort of try to construct the solution. And the solution we get to is the following. So the distribution function that I'm interested in, the probability that X is larger than A, is the determinant of a certain kernel. And the kernel is built out of the same objects that I already showed you. So this semi-group here is just, well, at least the one on the right, that's just a semi-group associated to a Poisson process, okay? The Q is the same Q that appeared before, and there's an object inside, okay, which is this QN epi, which is exactly the probability that I was telling you, okay? It's the probability that you go from, that the random walk goes from U to some point V, and that it ever goes above the curve. And now the curve is this initial condition. So if you remember yesterday from Jeremy's talk, the last thing he was showing was this KPZ fixed point kernel, and the KPZ fixed point kernel appears exactly in this way. Okay, so you have probabilities of a Brownian motion to, in that case, is to go below the initial condition. And for TASEP, what you get is exactly the same thing. So you get the probability starting from U, going to V, that you are going to go above, sort of hit the region above the initial condition, okay? And there's similar formulas for, so as I said, I just wrote the one-point distribution, but there's similar formulas for multi-point distributions. Okay, and I should also say that there's also analogous formulas not only for TASEP, but for various other variants of these processes where you can get the same sort of formulas. Okay, so I was going to try to give an idea of how this is proved, but since I took a bit more time than I thought, I will skip it. Let me just say that even though I showed you all this story about orthogonal polynomials and how this bi-orthogonalization works out, one in this case, in the case of TASEP, one can actually just check that you could think that you simply guess this formula in the way that I told you, and then you can just check that the Kolmogorov backward equations are satisfied. So that gives you another proof, okay? So you build this complicated object, but you can simply go ahead and check that the backward equations are satisfied. Okay, so I'm going to skip it, but that was the idea. Okay, so to finish, I want to very briefly tell you how the scaling limit works out. Okay, so this is the scaling limit that's going to take us to this Brownian scattering operator that Jeremy was presenting quickly yesterday. So the idea is the following. This is just very rough. So you have to fix some scaling, and the scaling corresponding, since we're looking at this probability, when you want to translate it into the probability of the height function, I mean, the scaling of the height function that you're looking at, you have to take a scaling like this. Okay, so you have to take t to be large, n is going to have to be shifted. Again, I did the same thing, but then there's going to be some position x and so on. But the nice thing is, again, we have all these objects which are explicit. Okay, so the first part of the formula, so this kernel involved this e to this essentially something like the semigroup for the Poisson process, and then q. And q happens to be related again to the Poisson process. No, sorry, not to the Poisson process, to the same objects. Okay, so q inverse is the identity plus this grad plus operator, where grad plus is simply applied to a function x, is f of x plus 1 minus f of x. Okay, so essentially you can write this piece here as you just sort of represent it as e to some power, and then you start doing expansions on top. Okay, so you just expand these discrete derivatives over there. Okay, and when you expand them, what you see is that the part that appears next to t becomes a third derivative. Okay, this is just an expansion on the size of the lattice. And the part, I don't know why I keep doing that, sorry. And the part that goes next to x becomes a second derivative. Okay, so what it means is that this left hand, the left factor, which is the part in red on the top, it goes to at least formally with this idea, after just expanding, it goes to this operator which involves the third derivative and the second derivative. Okay, so e to the third derivative times t and second derivative times x. So that's what appears on this red part. And the part in the middle, so this q epi, the one that involves these random walks, you just notice that in the scaling that I'm looking at, if you work it out, this scaling makes the random walk scale to a Brownian motion, and the initial data will scale to the limiting initial data. So essentially, all this problem about computing random walk heating times becomes the heating times for a Brownian motion. And well, then you have to work a bit to make all this precise. But essentially, this leads to the theorem that was, I guess, implicit in Jeremy's slides yesterday, which is that if you take this height function, then if you do the right scaling, this 1 to 3 scaling, then the limit define this limiting Markov process, which is the KPZ fixed point. And this KPZ fixed point has its transition probabilities characterized by a formula like this. So the probability that the height is going to be below certain heights at some points is going to be given by the Fredholm determinant of this kernel here. And that kernel is the kernel that this Brown may can go one slide further, just to say that the kernel, it's just built out of this STX, which is this object that I was telling you about with the second and third derivatives. And inside, what you see is the probability for a Brownian motion to go below the curve defined by the initial data. Okay, so just to summarize the whole story is that from this whole sort of mix between algebraic and probabilistic ideas that give you the solution of TASEP, okay, you end up with this formula that tells you that if you want to compute a probability such as the one on the top, okay, the probability, the distribution function for the KPZ fixed point, the way the initial data comes in is that on the right, you're going to have a Fredholm determinant of a certain kernel, but this kernel is going to be built out of Brownian motion. You have to solve the problem of how to compute the heating times of a Brownian motion to the same initial condition you are interested in. Okay, so just one more word is to say that, just to notice that in this formula, the dependence on T and X is relatively simple. It just appears in these operators, which are e to the 1/3 t d cubed plus x d squared. Okay, and the complexity about the initial data is hidden inside this problem here. Okay, so the good thing about this is that if you take this kernel, then you can easily compute derivatives in t and compute derivatives in x. Okay, because they just pertain to this simple part of the kernel. Okay, it's just this operator. So you start computing derivatives in t, computing derivatives in x. The initial data is not part of the story, and if you work a little bit, that's what leads to this KdV equation and the Kp equation that Jeremy was talking about yesterday. Okay, so that's what I wanted to say.
Okay, thank you very much, Daniel, for this very nice talk. And now we will listen to the discussion by Alisa Knizel. Thank you. Oh, okay, so please go ahead. So now we listen to the discussion by Alisa Knizel from University of Chicago.
Hello, everyone. So first I want to thank the organizers for the invitation. It's a pleasure for me to be discussing for Daniel's talk. And also I want to keep it in the form of an open discussion. So if anybody from the audience or Daniel has any comments, I'll be very happy to be interrupted. So in my presentation, I want to touch upon a couple of recent developments, which I find to be very interesting and exciting, which are closely related to what Daniel was talking about today and Jeremy yesterday. So the first, and also I want to talk about like some open questions, which I find like the most interesting personally. So one question is about the generalization of all the machinery and the results. So in particular, the convergence to the fixed point and also this connection to the KP hierarchy to other models. So this question, like Daniel briefly touched upon this in his talk. So so first is the natural question about the extension of the methods for the proof of the convergence, like beyond TASEP. like to the models which are close relatives. So in particular, the ones well, which are very similar, they push ASAP and push ASAP. So those are models where you like when the particle jumps and well, the side to the right or like to the left in the case of ASAP is not vacant, then like the particle pushes all the particles which are stacked in the block like in the corresponding direction. So yeah, like the natural question is like how to extend the results to these models. And like in particular, what exactly is special about the structure of these models which allows or like should allow this type of the generalization. Another like a natural extension in my mind is like towards the models which are the so-called quantized version of this model. So in particular QT-ASAP. So I would imagine that like this also should be possible on that level. So QT-ASAP is the model where the like now there's an extra parameter Q between 0 and 1 that defines you the rate of the jump. So the rate of the jump of like a particle in particular location depends on the number of vacant sites to the right. So this is what is QT-ASAP, and it's also in the KPZ universality. So yeah, so we expect to have the convergence to the KPZ fixed point here. So yeah, so those are some models like for which I would expect to see like the generalizations of the results. And like using the like similar methodology. Okay. Yeah.
So ask a question. Mm-hmm. So for QT-ASAP, is the transition probability determinantal?
Yeah, you can write the determinantal formulas in like in some way. I'm not sure if you can like do the like by orthogonalization.
No, so for QT-ASAP you can't, or at least as far as I know, nobody knows how to do it. So you have some determinantal formulas, but they're of a different nature. In a sense, the process is not determinantal itself. So you can
right. So my impression is that QT-ASAP is more like ASAP.
QT-ASAP is more like ASAP. Yes, it's in that level. So this method of exact formulas probably would not. I mean, it's not known, and one would expect them not to work. Now you can do other things. You can try to do other things, like in the case of QT-ASAP, something like what has been used for ASAP to show convergence. Maybe try to compare QT-ASAP with ASAP, but not through exact formulas, or making use of exact formulas, but not exactly through more analytical methods. Which is, I'm not sure if Jeremy mentioned yesterday, but that's something that was recently done by Jeremy and Shulaf Sarkar for ASAP. So maybe for QT-ASAP it's possible.
Yeah, so this is like exactly the second point which I wanted to mention, the generalization, like not through the exact formulas, but through a comparison argument. So this like, which was done to like large class of finite range asymmetric exclusion processes in this work. Like I think like mentioned by Jeremy yesterday and like by Daniel just now. Yeah, so like in particular, like for QT-ASAP, like as well. Yeah, like they're also like being like in the same work and also in the paper by Virag, like there was like shown also the convergence for the KPZ equation. So the question that I have here is my understanding is that like these comparison arguments, they work in the case of continuous time. So is it possible to do something similar in discrete time for discrete models?
Well, I mean, to begin with, you need a discrete model to compare with, but that can certainly be done because you can get the exact formulas for discrete models. Now the question about comparing, to try to compare with a non-exactly solvable discrete system, maybe that's better for Jeremy if he's around. But it sounds.
Hi. Sorry, my video won't start. Hi. It's possible. So it's not terribly clear how far these methods go. Like it's possible if you took discrete time TASEP, you could compare it to some finite range version. First, I'd have to find a finite range version to compare it to. I guess there are.
Sure.
I don't see what the discrete time would really change things except to make the thing kind of tricky to write down.
But don't you need generator?
Well, you still have a generator. I mean,
just looks horrible.
Yeah, exactly. It's going to look horrible. I mean, is there sort of an ASEP version of discrete time TASEP? I have to admit, I know almost nothing about discrete time TASEP.
It's just stochastic 6-vertex model.
Yeah, so I guess it's plausible this could work. It's not clear. We also use a lot of special properties of TASEP. I don't know if they're there for the other, like discrete time TASEP. It's really, there's some exact calculations going on in the middle of this calculation, which may not generalize.
So, and maybe I can point something out, which is sort of probably not the problem, but even simple things for discrete time are more complicated.
Yeah.
Some are easier, but for instance, this proof that I didn't have time to show, where I said, instead of doing all this algebraic thing, you just take the formula that you can say, okay, I'm gonna guess that this is the right formula, and then I simply check that the Kolmogorov equations are satisfied. That's actually a short proof that these exact formulas for TASEP are doing what they should do, that they are really the solution. So that can be done for continuous time TASEP. We don't know how to do it for discrete time. It certainly can be done because, I mean, we know they are the solution. But for continuous time TASEP, the checking the backward equations is very, very clean and nice. For discrete time, it seems to be hard. So there is an extra complication.
Thank you. And like, yeah, and of course, like, what happens, like the direction towards like the more general models where we don't have like the present of exit formulas, that's wide open. So so this is like the first part about the generalization to other models. Another question that I'm personally like very much interested in is the further applications of the exact formulas obtained in this work. So like in particular for the KPZ fixed point. So in a recent work by Corwin Hammond, Hegden, and Matetsky, like using in particular the these results about the formula for the transition probabilities for the KPZ fixed points. They studied the question about the maximizers of the KPZ fixed point for like quite a general class of initial conditions. So like the type of questions that are like probably natural. So in particular, they also studied the exceptional points, like the exceptional times when this maximizer is not unique. So like another question would be like, can you somehow estimate the number of maximizers at those exceptional times? And like just like more generally, like what other type of the information you can get from this like exit formulas, like about the process, and also like applications to other like related processes in the KPZ class. So this is like the second point, and like the last point is the applications of the connection of the established connection to the KP hierarchy. So in a recent work in physics literature by Pierre Ledoussal, he did the computations about the large deviations estimates for the KPZ equation directly, like using this connection to the KP. And like in particular, he recovered like many like recent results which were obtained like about the tails of the KPZ by such authors as Corwin, Gosal, Tsai, Claes, and Cafasso. So like there has been a lot of work in this area. So yeah, so like the question, like yeah, so I like personally don't know if like all of this can be like rigorous, can be made rigorous, or like this use of the connection to the KP, and like what are like other types of questions you can solve using this connection. So one of like, you know, like one of the natural difficulties I would imagine is the question about the well-posedness that was mentioned like yesterday in the Jeremy talk, like the well-posedness of the KP that one gets from like from the KPZ fixed point, but like in general, what type of the questions we might think of that will be suitable to the analysis, like using this like new discovered structure. Okay. Yeah. So those like the 3 points which I wanted to like mention, and like if you have any comments about that, I'll be happy to hear. Yeah.
Well, the last one about the well-posedness, that's a complicated question because so in this KP PDE that Jeremy was showing yesterday, the initial data is quite singular, but it's also maybe worse than being singular, is very far outside what's known in PDE as classes of initial data from which you can prove uniqueness. So that's so in terms of applications, if you want, of the KP, of this KP, that's a stumbling block because it just we don't have uniqueness for this PD. So we know that these functions satisfy the PD, but I mean, uniqueness seems to be out of reach for now. So I'm not sure about, I mean, one nice application which Jeremy mentioned yesterday very quickly is that you can see the Tracy-Whittem distributions pop out of these equations. And in that case, you have certain self-similarity of the solutions, which allows you to turn everything into ODEs, and then you have well-posedness in that case. So in the case of the special initial conditions are so similar, and they are the ones that keep popping out when you want to get simpler statements. So in that case, the self-similarity saves you, and you can prove a version of, if you want, of uniqueness, because you just get to a PD. But in general, yeah, it's not known, and it's sort of hard. So in that sense, it's a bit hard to use these equations to go further in this direction.
Yeah, I wanted to add that, like, even in that case, you know, if you look at the Hastings-McLeod solution of Palivate-2, it's not so obvious uniqueness. They prove it, but it's not a trivial thing, even there.
Yes. That's a good point. Yes. So in that case, it's known, but it has been given to us 20 years ago. No, probably more. But even in that case, it's hard, and in the general case, it's sort of quite complicated. So yeah, that's an open question, I would say. That's a real open question.
Okay. Yeah. Thank you very much. Are there like any other questions, like from the audience in the chat that I should mention?
I don't see a question in the chat. So maybe I can ask a question then. So if you say that you don't have uniqueness for these nonlinear PDs, so can you still use this PD somehow to prove properties of the fixed point, or so? Or do you just know that, because it seems like if you don't know that the question is well posed, somehow it's going to be difficult to use the PD, right? Or
Okay. So one thing that I should say is that the statement about these equations or about the fixed point solving these equations, I think it should be taken as a statement in itself. So it's an amazing statement. It's just the fact that, I mean, at least we wouldn't have expected it, that you have these that these finite dimensional distributions satisfy a closed equation, and that the closed equation is this famous integral PDE, and which sort of connects these growth processes to these dispersive equations. And we have no idea why, really. It's just a computation. So that's, there's sort of a deep question in itself, which goes beyond well-postedness and goes beyond trying to use these formulas for something. Mm-hmm. So yeah, the motivation comes from that side more than applications. Now, can they be used? Yeah, maybe, hopefully, but we have the problem of well-postedness. There's this example that Elisa was showing for large deviations for the KPZ equation, which is of the same equation, which was done by Pierre Ledoucet. Well, that's formal, but it gives you the right answer. So you can see things from these equations. But still, yeah, I mean, what else can be done with the equations? Maybe we'll find out. But for now, that's the story as far as it goes.
Okay, thank you very much. So thank you, Daniel.
I guess I just wanted to add, like, nobody said it's impossible to prove uniqueness of those equations. It's just that we haven't, this is a research project.
Mm-hmm. Sure. Okay. Thank you. So thank you, Daniel. Thank you, Elisa. Thank you to all the other participants.
Maybe can I have a very quick last question? So sure. This is just a super basic question. I'm not an expert on this at all. So I noticed, Daniel, that you were always working with the n-most right particle, right? But what do you do in the models when you don't have an n-most right particle, like with these, how we call flat initial conditions or something similar, when you have somehow infinitely many particles? So it's not a problem?
That's a good question. It is a problem. So these exact formulas really want to work only when you have a rightmost particle. So that's the world where they want to work. So what you do is you just sort of go, if you want to look at the flat initial condition, say, which is the fully periodic one, you look at the half periodic one, where you put just sort of particle hole on one side, but then nobody on the right, so that you're in the right position. And then you go very far to the right, look over there and take a limit. So essentially you just shift to the right position. And then what you have to do, and this is something we sort of have to work quite a bit to get in the paper, you shift very far to the right, and then you have to show that if you truncate very far to the other side, that doesn't make a big difference. And then in the limit, as you go to the KPZ fixed point, that disappears. So you get the focus. But for the KPZ fixed point, looking at sort of two-sided things is completely fine, and the formulas are nice. For TASEP, formulas want to work in the case you're pointing out. So just when you have right formulas, but then you can sort of, by taking a limit, do it.
Okay, thank you.
Okay, so I think, so thank you again, and I think we will